Hey, ladies and gentlemen, this is our second example. We're going to take a look at the website that was included in the explanation video that went along with Strang's section 7.3. So recall this is the principal component analysis website that we have discussed already. It's the one that provides the two-dimensional and three-dimensional examples, and then it goes into this 17-dimension example. And this is what we're going to look at. And what we want to do is we want to understand what the data are. And then we want to recreate this graphic and talk a little bit about what this is and just as important, what it is not. So first things first, let's talk about the data. Remember, always the same, step zero. So step zero is understand the data. We need to understand and we need to make sure that we structure the data correctly. So when we build our data matrix, just as a reminder, we have the features across the columns, and then we have the samples down the rows. So we have samples down the rows, and we have the features across the columns. So first things first, we need to look at the set of data here and decide what are the features and what are the samples. So I've recreated the data here. It's a little bit easier to read. These are several different items where they have gathered data for 4 different countries. And in order for us to figure out what the features are, we need to think, what are the samples? What are the experiments? What are the observations? So every one of these rows, if they're observations, needs to be collecting data on the same thing. So are cheese and confectionery 2 versions of the same type of observation? Or are England and Northern Ireland 2 versions of the same types of observations? It's pretty easy when we start to ask these types of questions to realize that for England, we've gathered all of this data. We have the data on 17 different food categories. And then the next sample is Northern Ireland, where we gather the same data. We could think about the samples are the countries. And the things that we are sampling, the features, are all of these categories of food. It doesn't make any sense to think about the fresh potatoes are a sample across these countries, but then fresh vegetables is another sample across the countries. Those are different things, right? The fresh potatoes and fresh vegetables don't necessarily have anything to do with each other, whereas these are all countries, and those are what we're using for samples. So it's important for us to understand in this particular situation, we are going to build our matrix, and it's going to have 4 samples, and it's going to have 17 features. So to visualize this correctly, what we would do is we would grab this and we would copy it, and then we'd put a paste in. And you may be familiar with this, you may not, but in Excel, one of the paste options is a transpose. And we can transpose when we paste, and this is the actual format for our data. These are the features, the different types of food, and the samples are through the country. So what we're going to end up with when we build our covariance matrix is we're going to end up doing our dot products countries against countries, and we're going to have a 17 by 17 features versus features covariance matrix. And we can see why they haven't put the data down in this fashion. It's difficult for us to see with all of these different columns. But we have to make sure that we have everything correct. So let's go back and take a look at MATLAB. And in MATLAB, we'll take a look at the data matrix. So the data are in, I've just put them in matrix A. This is what the data look like. So now that we have the data all set up, what's the next thing that we need to do? We need to mean center the data. And what that means is that for each feature, we are going to take that set of data and shift it onto being centered around 0. There's a very handy command in MATLAB called mean. If I do mean A, it will do the column by column mean for whatever matrix we have. So mean A is already set up to deal with the type of data in the format that we are using it. And so it's as easy, mean centering, as taking A minus the mean of A. And that's going to give us data that are centered on 0. If we sum up the values in any one of these columns, it's going to be equal to 0 because that's what we've done for our data. So the other thing that we discussed, so we talked about this being step number 1. We're going to mean center at 0, and then we're going to make the decision whether or not we want to standardize, whether or not we want to bring the variance in to be 1 across all the features. To do that, what we would do is take our mean centered data. So I'm going to call this A mean is equal to A minus the mean of A. And this is now the mean centered data. And what we would do to make A standard, this would be standardized, normalized, is we would take A mean and we would divide by the standard deviation. So when we do standard deviation, and let me show you. So if we do STDA, again, it's built for the type of analysis that we're doing. MATLAB takes the column by column standard deviation. And so what we're going to do is we're going to divide through by that standard deviation for each column to take the data. Even though these are mean centered, you can see some of them are varying just in the teens, some of them are varying in the hundreds. So maybe we don't want that variety. Maybe we want to standardize it all. So then what we would do is we would set up our A standard, and that would be the mean centered data. So we're going to take A mean, and then we're going to dot divide by the standard deviation of A. And now what we have is we have data that are centered at 0, but you can see all the values fit into the kind of the general parameters of a basic normal distribution, which is centered at 0 with standard deviation of 1 or variance of 1. And now we've brought all of the large variations down so that all of the categories are equalized. And we'll talk about why we would perhaps want to do that or not want to do that. We're going to start without that. We're just going to look at the mean centered data. And then what do we need to do? We need to build that covariance matrix, right? So we talked about this. C is going to be the mean centered data, and we take A transpose times A, and then we divide by the number of features minus 1, which in this case is 17 minus 1. And what we're going to end up with then is a 17 by 17 matrix, which is our covariance matrix. And all these values are multiplied by 1,000. So we have some larger covariances. This is 523. And then we have some small covariances, right? This is 10, a negative 10. So all of the covariances, that provides us with the path to understanding the principal components. We can go through then and we can calculate our loading vectors. And the loading vectors are going to be the singular, or rather the eigenvectors of the matrix that we have here. We can also do that simply by calculating the singular value decomposition, right? So let's do X and D is equal to I of our C. These are the eigenvalues that are non-zero. All the rest of them look like they're pretty close to 0. Again, this is 10 to the 4th. We can actually just take a look at the diagonal values of D, and these are our eigenvalues. And perhaps we can see it a little better with a long format. And let's take a look at it this way. These are the eigenvalues that we have. Most of them are 0. Does that make sense to us? Right? Our matrix is 17 by 17. But what's the largest rank that that matrix can be? Our 17 by 17 matrix can't be larger than rank 4 because our original matrix that we used to build this has at most rank 4. And what we can see is it's really rank 3. The rest of these are, for all intents and purposes, 0 up to the rounding error. And these are our eigenvalues. And so associated with the largest eigenvalue is our principal component 1 loading vector. So if we take a look at in X, the last, because this is the last singular value or last eigenvalue, this is the way that MATLAB does it. It gives us that largest value at the end, unlike singular values where the largest value is at the beginning. We've got to keep that in mind. What we're going to do is take a look at the vector associated with that. And here's our loading vector. So if we take the loading vector and multiply it times our data, we are going to end up with the principal component. So we've solved. Let me write down the steps. So step 2, we built the covariance matrix. The covariance matrix was A transpose A divided by 17 minus 1, which was 16. Remember, the A has already been mean-centered. Then step 3 was to apply the eigenvalues and eigenvectors. So what we did was xd is equal to ig(c). And then we found the largest eigenvalue in the D matrix, which happened to be the last one, and we pulled off that first loading vector. So the first loading vector, v1, was equal to the last vector, the one that's associated with the largest eigenvalue. And this is the loading vector for principal component number 1. And then finally, we build the principal components. So we can take this loading vector and multiply it times our matrix. And remember, we talked about this. There's really 2 options here. So we can build principal component 1 as the mean-centered data, A, where we've taken the data and shifted it over to be centered at 0 for each of the features. And we can multiply that times V1. Or we could take our original data and we could build principal component times the original data matrix, recalling that we have defined A to be equal to D minus the D, let me call it bar. That's the notation that Brunton uses, where we are subtracting off the means for each of the columns. Well, what we're trying to do is recreate this picture. And we don't know what they've done. Or recreate this picture. This is part of what you're going to do in the homework. But we don't know which of these principal components they've actually calculated. So let's take a look. We'll do each of them and see what we get. So this was the answer. Let's actually call this V1. This is our first loading vector. So if we take our A mean times V1, that's going to be principal component 1. Principal component 1 looks like this. Got a negative 477, and then we have 3 positive values. And let's take a look at what that looks like. 477 and 3 negative values. So why doesn't ours match? Remember, V1, the right singular vector, the loading vector, could be the negative of that. I could calculate this as negative because I could take the negative of V1 as long as I also multiply U1 by a negative as well. So I could come up with this set of values here. 477, a negative 91, 145, and 240. And that looks exactly like what we have here, 91, 145, and 240, a positive 477. So they have applied, for their principal component, they have calculated the principal component as it's been applied to the mean-centered data, not to the standardized data. If it was to the standardized data, we wouldn't match up with their values. Let's do the same thing for principal component number 2. So go back to looking at the values of the eigenvalues, and the second largest eigenvalue is the one that's associated with principal component number 2. Remember, the eigenvalues are telling us how much of the variation is explained by each of the principal components. We already talked about that. So what we're going to do is we're going to set V2 is equal to X, which is the eigenvector matrix. And then we're going to do n minus 1. Similar to what Python does, we can grab the second to the last, and we can set that equal this way. And then we can build principal component 2. Principal component 2 is the mean-centered data times V2. And we end up with negative 286, 244, about 59, and about 2. And we can see, looking at the values here, that these values along PC2, principal component number 2, actually match up with what we found. Using principal component 1 and principal component 2, we can come up with a graph that matches what we have here. And this is the graph using the principal components that we calculated. And it's a lot easier to see because you have to go to the website to see this well. But we have a graph here that matches exactly with what's going on down here. Let's talk a little bit more about whether or not we want this. This is how it's presented at the website, but this is not the only option. Let's go back to the data for a minute and talk about whether we want to standardize or not. So these are the data, and we are not standardized, which means that even though we've mean-centered, right, and remember we have the features here, we have this matrix transpose, we're mean-centered. The question is whether or not we want to maintain the information associated with the actual size of the numbers. In other words, the confectionery numbers may have a large amount of variation, but the numbers themselves are somewhat smaller. Do we want to think more about the variation, or are we also interested in the size of these numbers compared, for example, to the cereals, which are much, much larger numbers? Do we want to retain the size of the numbers in our analysis, or are we only interested in variation? If we're only interested in variation, then we want to use the standardized data. We want to take the large values and the smaller values, and we want to equate them so that we look only at the amount of variation within the data. That's a question that has to be answered. There is no right or wrong answer to that question. It's just something that we have to decide for ourselves. So if we go back and take a look at, and I'm not going to walk through all the steps again, but if we come back, we can do the same exact work that we did over here, but instead of using the mean-centered data, we'll use the standardized data. We'll use the data matrix, a standard that we created, where everything has been not only mean-centered, but it's also been brought in so that the variance in every feature is 1. And then we'll look and see what happens with that. That's what I'll do, and I'll show you. All right, so I've rerun the problem, and what I'm showing you here, a graph similar to what we were looking at before, but now what we have is we have principal component 1, principal component 2 that are built based upon the standardized mean-centered data. And we have a distribution that looks different from what we had previously. Right? It doesn't appear to be the same type of distribution. The big difference is the Northern Ireland is no longer kind of in the middle for PC2. It's actually an outlier even more than Wales is with respect to principal component number 2. So what I'll do now is I'll show you the comparison between the mean-centered and the standardized to give you an idea of kind of what the difference is with each of these. All right, so what we have here are the principal component 1 versus 2 graphs, just like we have down here. This one, remember, that's at the website, they mean centered. So we have 0 for the means. This is no longer applying the loading vectors to the mean centered data. This is applying the loading vectors to the original data, just like we did down here. We have to do that in order to have a good conversation when we're talking about the mean centered versus the standardized, because the variation in the mean centered data versus the standardized data is significant. So in order to compare apples to apples, we're going to apply the loading vectors to the original data. And that's what we see here. So what we see is the mean centered standardized data is in blue. And then just the mean centered data is the original magenta. And this gives us the indication of what we saw previously. These are the data that match up exactly with what we have in the website. And then the standardized data, you can see Northern Ireland for principal component 2 doesn't change very much. But Wales and England, and to a lesser degree, Scotland, all drop when we standardize the data. So again, whether or not we have to have mean centered data. We have to do that in order to calculate the covariance correctly. That is a requirement. Whether or not we standardize the data depends on what questions we are asking, right? Do we want the confectionery number and the cereals number and the difference in magnitude to be represented as it is in the magenta? Or are we only interested in variation across these features as we see in the blue? That's something that every researcher has to address. So this is just an example of how we apply the steps here in order to come up with the principal components and what that looks like and how we can match it up against results that we can find online. That's it. We look forward to seeing you in class. Thanks.